today's speaker at the Rutgers Experimental Math Seminar is Professor Dr. Manuel Kauers from Linz, from Johannes Kepler University at Linz, who will speak about how to multiply matrices as fast as possible, and in many ways, not just one way. Okay, please, Manuel. Manuel? Oops. Manuel, your turn.
He may have disappeared for a moment.
Okay, so please be patient. Okay, so let me just make an introduction. And so people who are not familiar with matrices. The traditional algorithms for multiplying two matrices is cubic. And there was a big breakthrough of Volker Strassen in the late 70s that broke the n cube barrier. Now it is log base 2 of 7. And then it was a race to improve the exponent. And
looks like he's back now, Dr. Z.
okay.
Here I'm back.
Okay, great. So Manuel, please.
Okay, thank you. So I'm sharing my screen.
Yes.
Can you see it? Thank you all for coming, and thanks to Doran for the invitation. It's always a pleasure to speak in the Experimental Mathematics Seminar. It's even more a pleasure when I'm physically there, and I hope that one day in a not so distant future this will be possible again. But even so, this is better than nothing. So I'm going to tell you something about matrix multiplication. That's probably a topic that we can all relate to in one way or another. So here is the matrix multiplication for the case of 2 by 2 matrices.
Sorry to interrupt. Robert, you're recording, right?
Yes, I am recording.
Okay. Thank you.
Okay. So this is the way how you learned it some time ago, and how you are teaching it to your students. And if you count, you find that you need to make.
So excuse me, I think because we're seeing a terminal. Is this what you want to show us? Yeah, no. I doubt it. Yeah. Thank you.
Sorry.
Yeah. I say it because I've had this issue before. Zoom has these issues with what is it showing. Yeah, thank you very much.
So yes.
Sorry to interrupt.
No, thank you for pointing it out. Okay. So here, this is the matrix multiplication that you are used to. And if you count the yellow dots, they are the products that you have to execute, and there are 8 of them. You have to do it with 8. You have to do 8 products in order to multiply 2 by 2 matrices. And there's a way of doing it with 7, and here's this. So it turns out you can write the entries of the product matrix as linear combinations of certain m's. There are 7 of these m's, and if you have the m's, then there's no multiplication needed, but you need 1 multiplication to produce each of these m's. So here's the definition. So it doesn't matter what exactly the formulas are, but the point is that each m is a linear combination, is a product of a linear combination of the a's and a linear combination of the b's. So each m requires 1 multiplication, and since there are 7 of these m's, we are saving 1 multiplication. We need only 7 instead of 8. So this is the cool observation that Strassen made 50 years ago. Now, why is this so cool? Because if you look closely, you recognize that not only do we save 1 multiplication, but we add a lot of additions instead, and that in total it makes it worse. But if you think of the entries of the matrix not as numbers, but you think of them as themselves also being matrices, then you realize that adding 2 matrices is cheaper than multiplying 2 matrices, and so we may be willing to trade a single multiplication for a lot of additions, because it may pay off if the matrices are really large. That are so if this is a block matrix with very large blocks. And then moreover, if it's a block matrix with large blocks, then you can play this same game with the blocks and multiply the blocks in the same pattern and do this recursively. And then this turns out to become an algorithm whose complexity is not cubic anymore, but it has a very strange exponent, log 7 to the base of 2. So log 8 to the base of 2 would be the 3, the usual classical 3. And this is the beta exponent. So it's not just a constant factor improvement, it's really some improvement that gets better and better for larger and larger matrices. But this is a strange exponent. We don't usually see such exponents. And so the question arises whether this is the best possible exponent. And we may have believed that 3 is best possible because 3 is a reasonable number, but this logarithm is not a reasonable number. So we can ask if we just define omega to be the smallest exponent so that you can do matrix multiplication in n to the omega, then what is this omega? What is the smallest possible exponent with which you can do matrix multiplication? And so we know it's less than 3, but what is really the smallest? And yeah, there has been a lot of work after Strassen until...
I have a quick question, I'm sorry.
Please. Yeah.
So when you say operations in the ground ring, you really mean multiplications or also counting additions there?
Also including the additions.
Oh, okay, thank you.
So it turns out that if you count whether you include the additions or not just influences the constant factor that is hidden by the O. So it doesn't matter. Okay, so there was a lot of work, a lot of people who looked into the problem and improved further, and the algorithm became more and more complicated, and the matrix sizes from which on they become efficient gets larger and larger. And then at 1990, it somehow was stuck for about 20 years, and then it continued. Some people looked at the ideas from the 90s and pushed them a little bit further, but you see the last improvement from 2014, that was in, I don't know what is that, the seventh decimal digit. And remember, that's the exponent. So this is completely useless. This is nice theoretical result, but nobody will use any of these algorithms for actually multiplying matrices, except for
does MATLAB use, for example, Strassen's original algorithm? Does any of the software?
Yeah, so that's what I'm saying. The first one is really used in practice. So
Strassen's is used in real life.
Is used in real life, but all the others are not. So this is also what you read in textbooks. They just copy from older textbooks, and then they say Strassen's algorithm is only of theoretical interest. That's not true anymore. So Strassen's algorithm is really used, and it pays off from matrix sizes of size maybe 100 or so. So that's not too big. But then the other ones, they are so far only of theoretical interest. And so what we could, the starting point of this project is can we find a matrix multiplication that beats Strassen's algorithm? Maybe not in the exponents, or maybe not theoretically, but somehow from matrices of reasonable size. And so the idea is, what about if we don't divide the matrix into 2 by 2 blocks, but into 3 by 3 blocks? So, and then apply this recursively. Then we would need a certain pattern for 3 by 3 matrices, right? So the question is, what's the smallest number of multiplications that you need to multiply 3 by 3 matrices? And yeah, okay. So I'm not the first to ask this question, but I'm also not the one who has the answer. It's an open problem. Nobody knows how many how many multiplications are needed to multiply 3 by 3 matrices. So here are some things that we know. One thing is you can do it with 27. That's the naive algorithm. And you can play a bit around with Strassen's algorithm and say, oh yeah, 3 by 3 matrix contains 2 by 2 matrices, and for this we have something better. So if you play around with this, you get down to 25. Maybe if you're very clever, you get down to 24. And the best thing we know is from the 70s, this is 23. So we can do it with 23 multiplications. And there's also a lower bound. There's somebody who showed that you need at least 19 multiplications. And so this is the number that enters into the exponent. If we apply this recursively, then we will get the exponent log to the base of 3, and then this number. So, and if you want to get a smaller exponent than Strassen, and you have to do it with 21, which is a bit annoying because that's exactly between 19 and 23. So the question is...
I'm sorry, I have a very quick question.
Yeah.
If you were able to do the 19, how would it compare with the other omegas? Like, would you be the best omega, or would you? No. Where would you be?
Not by far. You would just beat Strassen and perhaps the next one, but you would not get really down.
Okay, thank you.
Also, in the case of 2 by 2, is 7 known to be a lower bound also? Like Strassen
Yes.
does 7. Oh, okay.
So for 2 by 2, we know a lot. For 2 by 2, we know that Strassen's algorithm is the best. You can't do it with 6. And we also know that although there are several ways to write down Strassen's algorithm, all of them are somehow equivalent. So there are not 2 distinct ways of doing it with 7. There's only one way, essentially, to do it with 7. And that's different here. So in the 3 by 3 case, it turns out you can do, we don't know if 23 is optimal, but what we do know is that there are several distinct ways of doing it with 23. And I will explain later what that means, distinct ways. But somehow maybe that's an indication that maybe it's not optimal. It's just we haven't found the 22 yet, and not to speak about the 21 case. In fact, there are infinitely many different ways. There was somebody who wrote down a family of such multiplication schemes that involved parameters. And when you set anything to the parameter, it gives a completely different multiplication scheme. But so that this involves fractional coefficients, and there's a 1/2 and a 1/3, and maybe that's not so nice. If you restrict to multiplication schemes with only coefficients that have plus 1 and minus 1, then what we knew were only 3 other schemes. So there's 4, together with the Laderman scheme from the beginning, 4 ways of doing it with 23. And so what we have done is we used computers and compute a considerable number of additional ways of doing it with 23. So I didn't update the slides. So by now it's 17,000 new ways of multiplying 3 by 3 matrices with 23 multiplications. And we expect that this is only the tip of the iceberg. So we stopped this computation because at some point we were exhausted, and not because we didn't find anything more. So we could let this run, and it would probably continue for a long time to find new ones. So then the obvious question is, did we find something with 22? No, we didn't find anything with 22. Of course, that's what we wanted to find, but we didn't. We didn't find anything with 22. But still, the more solutions there are with 23, heuristically, it becomes somehow more likely that this is not the optimal, because we expect the optimal to be essentially unique, like with Strassen. So what these 17,000 new ways indicate is that maybe there is something out there and we just have to find it. So how can...
Manuel, the lower bound of 19 uses some lower bound techniques. So did people try to make it 20 to use the same techniques to make the lower bound higher?
Yeah, I don't know exactly how this works. Probably they tried, but I don't know exactly what they do to get these bounds. I know they use algebraic geometry, but I haven't looked into how exactly this works.
Okay.
So how can we search for such a scheme? So we do something that Doran teaches us whenever he has the opportunity to do so. We make an ansatz. So we know the pattern of what we want to find. So we know we want to find certain m's so that we can write the c's as linear combinations of the m's, and each m is a product of a linear combination of the a's and a linear combination of the b's. So let's just make an ansatz with some undetermined coefficients for all these linear combinations. Linear combination of the a's, of the b's, and then finally of the m's. So the undetermined coefficients here are the alphas, the betas, and the gammas. And then you say, well, the c's should be related to the a's and the b's in the way that matrix multiplication works. And then you equate coefficients, and then you get equations for the alphas, the betas, and the gammas. And so if you work out the math, then you see the equations, you can write them down in this way. Never mind about the details. So that it's a bit unfortunate that I have alpha, beta, and gamma as variables, but the delta is not an additional variable. The delta is the Kronecker delta on the right-hand side. So you have a lot of equations, and they are cubic. They are of degree 3, and you have a lot of variables. But in principle, that's it. You just have to solve this algebraic system of equations. And the problem is this is very difficult. There are lots of variables and lots of equations, and you can't just throw this into Maple and expect an answer. Laderman, somehow in his paper, he claims that he solved this system by hand. And he says he will explain in a forthcoming paper how exactly he did it. But he never wrote that forthcoming paper. So we don't know how he found it.
He's probably a liar.
Yeah, maybe. But yeah, somehow he found a solution, and we don't know how he found it. So one idea to simplify the problem is do everything mod 2. So then you don't need to distinguish between plus and minus, and you just need to distinguish 0 and non-zero. That reduces the search space a little bit. And when you compute modulo 2, then you can also translate it into logic. You can translate it into the satisfiability problem by reading the times as and the plus as XOR, and then translate the XOR into an OR, and then use a SAT solver. So a SAT solver is maybe, okay, that's an NP complete problem. So maybe a few hundred variables is a lot. But SAT solvers are very strong nowadays. So they are used for industrial size problems with millions of variables, of course, somehow structured. So why not try? And so this is then where my collaborators come in. My wife, Martina, and a collaborator from her team, they know how to deal with these SAT solvers. They don't usually care much about matrix multiplication, but they know how to deal with the SAT solvers. So we work together and then use the SAT solvers to solve this system. So that requires lots of technical things that I don't want to explain here, maybe not so interesting, but with the right way of encoding it and with using large computers, we were able to find like several solutions per minute. And then the question comes back to us, to the mathematics side from the computer scientists, and are these really new solutions? So you get one solution per minute, but what does it mean to be a new solution? So then, coming back to what I said earlier in response to a question, Strassen's algorithm, I said, is essentially unique. So in which sense? And that means here in this case, in which sense are these really new solutions or maybe not new solutions? And what you have to take into account is that there are symmetries in the matrix multiplication problem. So if you have a way of computing the product of A and B to get C, then you can, you can modify it a little bit. You can insert a constant matrix in the middle and its inverse, and then you get a matrix multiplication scheme. So that would amount to modifying the m's a little bit. So then it looks different, but it's still the same. And once you have this, then you can also do this, and you can do this. Oh, and then you can do this also. You can exchange the roles of A and B if you also transpose A and B, and that also changes the way it's written down, but it doesn't essentially change the multiplication scheme. Oh, and then there's one more symmetry that I can't write down so easily, but it's a little bit more subtle, but otherwise of the same nature. So there is a group, a symmetry group on the matrix multiplication problem. And we would say that a solution is really a new solution when it's not in the orbit of one of the solutions that we have seen before. So, oh, yes, and also you can commute the m's. That there's no reason why the fourth m should be the fourth m and not the seventh. So that adds a lot of trivial additional symmetries that you can use to normalize and to compare. Have you seen that solution or a similar one earlier? It's a large symmetry group. It has 10 to the 30 elements, but on the other hand, 10 to the 30 is not so much when you compare it to the whole search space, which has 10 to the 100 and something candidate solutions. Okay, so we consider a solution as new when it cannot be mapped to an earlier seen solution by one of these symmetries. And the 17,000 solutions that I announced, they are new in this sense. They are mutually inequivalent. And then you can use also the symmetries for simplifying.
It's very fast to determine the equivalence class and to determine whether two things are equivalent.
It takes a few seconds. So I know if that qualifies as fast, because you have to do a lot of times. So yeah. And there's a way of making it a little bit faster, because you can write down certain invariants. You can look at ranks of certain matrices, and then they are easy to compute, and then compare these invariants first, and then you have a quick check that something is not equivalent. So if things are not equivalent, then you can usually, that will be quickly detected, but when things are equivalent, then you have to do a more intensive check, and this takes a few seconds. Okay, and then you can use the symmetries also for simplifying. So by saying the subsolver has found something, but now let's apply some random group elements to see if it leads you to some other representation of the same solution, but some maybe with fewer additions or with fewer coefficients when you write it down. And we have done this as well to make the solutions a little bit more simple. Oh, and then remember, we went down to 2 element fields, but we are really interested in integer solutions, solutions that work for any ring really. So the next thing that we have to do is take these mod 2 solutions and lift them back to the integers. And here's how we did that. How's the time? Oh yeah, time is good. So remember, these were the equations that we had to solve. And so suppose you know a solution that is mod 2, so it consists only of zeros and ones. And we make an assumption. We make an assumption that it came from an integer solution, and the integers appearing in the integer solution were just +1, -1, and 0. So that's an arbitrary assumption, but we make that assumption. And then we say, okay, we know then that the zeros are really the zeros. And the only thing we have to find out is whether the ones are +1s or -1s. And so what we do is we accept the zeros as the zeros. And for each of the ones, we put a variable, a new variable, and a new equation that says it's a +1 or it's a -1. And then we get an algebraic system that has much fewer equations and much fewer variables, still a lot, but few enough that we can do it with Gröbner basis. And then with Gröbner basis, then we can solve this system over Q, and then we really see where are the +1s and where are the -1s, and we get a system, a multiplication scheme that works in any ring. Now you may wonder if this is a fair assumption. If I have a solution that works mod 2, why should it come from an integer solution? Why should it not come from an integer solution that contains a 5 somewhere? The answer is I don't know why that should be. And in fact, it's not always the case that a modular solution can be lifted to an integer solution. But for some reason, it's almost always the case. So there are only very few where it doesn't work. In almost all cases, we could translate them back to the integers. Oh, and then there's one more thing that we can do with these solutions. We started to play a bit, and we said, okay, what can we do? If you look at once more at these equations, you see the problem is that these are cubic equations. They are degree 3, and that's not nice. It would be much nicer if they were linear equations, because linear equations doesn't matter how many variables there are, we can solve them. But imagine you have a solution. If you have a solution, then you can play with it and say, okay, I take the betas and the gammas of the solution and I throw away the alphas. I replace the alphas, although I know the alphas, I replace them by variables. And then you get a linear system. So what if you solve this linear system? Okay, you will get back the solution that you started from. That's not surprising, but interestingly, you get some other solutions. You get an affine space of solution it's not just a single point. It has some positive dimension. So that means you can introduce free parameters into the matrix multiplication scheme. And so that brings you I've been reporting about 17,000 solutions, but this here brings you infinitely many additional solutions. Oh, and then you can do this with the betas also and with the gammas, and you can repeat this and introduce more and more parameters into the scheme. So we played a little bit with this, and we found several families of matrix multiplication schemes that have up to 17 parameters in them and coefficients in the integers. And we can use Gröbner basis to check that these parameters are really algebraically independent. So it's not just that there's a +x minus x somewhere, but these are really independent parameters. And that says something about the solution set. So all these matrix multiplication methods, they live on an algebraic variety in a very high dimensional space. So what was the number of variables? 600 and something. And what is the dimension of this variety? Not known. We don't know. But what we can tell is the dimension is at least 17. And that improves the earlier result from this person I mentioned from the 80s, whose solution had only 3 parameters. So the dimension is now at least 17, and before it was at least 3. Probably the dimension is much higher, but we can't tell. But knowing something about the geometry of this variety, that we hope that at some point it will help. It will guide us to a solution which has only 22 multiplications, because maybe these solutions, they live at the singularities of this variety or something like this. But so far that none of these approaches were successful, but we are not yet at the end of our ideas. Okay, so little bit fast, already getting to the conclusion. So let me summarize. So what we did was find a lot of additional multiplication methods for 3x3 matrices that require 23 coefficient multiplications. And we have shown that the dimension is much larger than it was known, but nothing of this has any immediate implications on the complexity of matrix multiplication, neither in theory nor in practice. Also the known multiplication schemes for 3x3 with 23 multiplication, they have fewer additions than any of ours had. So there's no improvement in any sense with regard to actual computational cost. It just says something about the structure of the problem, perhaps, hopefully. And in particular, we don't know if we can do it with 22 multiplication. And if you find such a scheme, please make sure to let me know, because I would be highly interested. You may want to have a look at the actual solutions that we found, and if you want, you find them on this website. So we've prepared them here. So this, let's say this is the beginning. Here's some information about how it's encoded, and then here you see the some of these invariants that I mentioned, and then here there is a solution. It's written down in a notation that I didn't explain, but somehow these here they are the m's, and here it's encoded in which of the c's this m enters. It's the m1, the m2, and so on. So then you see there are really a lot of them, and if you scroll down here, and here you find these families that I mentioned. I think I can't open them now because it wouldn't look very nice. Yeah, let me not open them, but it will look like it. Conceptually, it would look like this, except that there are also x's in them that somehow magically cancel out if you do the matrix multiplication. All right, so that would be the end. And happy to answer some questions if you have any.
Please unmute yourself to applaud Manuel, and then we have questions.
Thank you very much.
Manuel, I'm really very impressed how many ways you can do this thing. But first remind us, if you make it, if one day you have 22, would it break the current record, or it's only for 3x3?
Yeah, so for 22 would still be slower than Strassen.
So you're focusing on 3x3. So
yeah, it would only improve the 3x3 case, and 21 would improve Strassen.
And the other improvements to Strassen, they use the same methodology?
Yeah, somehow, but they divide into not 2 or 3 subdivisions as we have discussed here, but they divide into hundreds of blocks, and then use some existence theorem that said that they don't really explicitly write down the m's. They just say, oh, if you do such a division, then you can do it with this number of m's, and so there must be an algorithm that has this complexity.
So it's cheating. It's not implemented.
No.
Oh,
no.
So it doesn't count. Okay.
It's not implemented, and it wouldn't be reasonable to implement it, because if you just estimate how big the matrix would have to be. So these are really these crazy algorithms that have a very large constant in the O. So there's no point of implementing.
Oh, so that's a stupid game. Okay.
Yeah. So this is for the omega. So yeah.
Any questions from the audience?
Yeah, I have a question. So you haven't found the 22 or the 21, let's say, but do you guys have a guess or a feeling for what you would think? Like, what would be your personal conjecture on this? What is there any intuition to? I think it's 22 because of this and this, or
Yeah. So our argument is that 23 is not optimal because we expect the optimal one to be essentially unique. And since there are so many solutions with 23, the more solutions you find, the further it is away from unique. And the more is our hope that this means it's not the best possible.
But do you think you could formalize that? Because let's say if you could come up with a proof where you just formalize that statement, where like, oh, if the optimal were to exist, then you could not have more than so-and-so symmetries, and then you would be able to at least prove existence by showing that you found more than what could happen for the I mean, just me completely guessing here.
So I wouldn't, I don't see how to do this. I mean, it's really just a feeling argument. I don't see how to formalize this.
Okay.
No, yeah. So the hope is we would actually find one. And
yeah, of course.
And then maybe the families that we find guide us to where to look for it and make the search more efficient. And so this is something that we are thinking in this direction.
Yeah. But thank you. Very good presentation.
One quick question. What about 4x4 or 5x5?
Oh, yeah. So yeah, that's interesting. 4x4 is easy because you can do Strassen twice.
Yeah.
And that's the best we know. But for 5x5, there was a paper in the 80s that said, so you need, how is it? The naive algorithm needs 125, which is 5 cube. And there was a paper in the 80s that said you can do it with 100 multiplications. And then just last year, there was somebody who said 99 also works. So there are people looking into this.
And log to the base, 99 to 125.
No, it's not. It's not enough. It's not enough to beat Strassen. You have to get down to, I don't know, 92 or so. So if you go on, so we discussed 3, and then you asked 4, 5, 6. So the first one where we know you can beat Strassen is 71. So yeah, so it's not. It's quite a large number of blocks.
More questions from the audience?
Sure, I have a question.
Go ahead.
So you said that you'd found 17,000 sort of distinct schemes, and at this point you had found more than 17,000, perhaps. Is there any idea of how many there are, an upper bound of how many you expect to find? Or is it just sort of an enormously large space and we're not sure?
I don't think that we are anywhere near the end. I think the number is like in combinatorial problems. It's you will be able to write down the number maybe, but you will not be able to list all of them because the number is so big. And that's just based on once we found the way to enumerate them, just how quickly they come. And it's always a new one, and it doesn't get slower. And you look at them, and you always see it's somehow 90% of them, of the things that the solver finds, are equivalent to things that you have seen, and 10% are new. And naturally, you would expect that this 10% gets smaller at some point when you get near the limit, but it's constantly 10% of the things are new. So I think we could play this game for a very long time. And this 17,000 is just related to what we did and not related to the actual problem.
That 10% are new comment makes me wonder, are you finding that the ones that are equivalent to ones that you found before tend to be equivalent to the same few a bunch of the time?
Yeah, but that's also related a bit to the technique that we use, because I said that even for a SAT solver it's a hard problem. So we play some tricks, and one of the tricks is we start from a solution that we know, and we delete part of it, and then we give it to the SAT solver, and then it completes the thing that we deleted, but not in the way that we started from. Usually it finds something different, but it's a solution that in some sense is near to a solution that we already had. And solutions that are closed, they have a certain chance to also be equivalent to a solution. So it's not that we take them completely uniformly distributed from the solution set, but we are going through neighborhoods and see, oh, there's something close by and there's something else, and so and that's why we find so many solutions that are equivalent to things that we have seen before.
Another quick question. Was your idea to apply such solvers to this problem?
No, actually there was one person, there was one paper before. Yeah.
And are such solvers used for other purposes, for example, to solve the affine equations and other applications outside logic or computer science, similar to yours?
Yeah, so so this collaborator of mine, who's also Marijn Heule, who was mentioned on the title slide. I can go back to the slide. So he uses this for solving combinatorial problems. So he made, maybe you saw that on the news in the States a few months ago. He made he proved a conjecture about Ramsey number 5 by solving reducing it to a combinatorial problem and then doing the combinatorial problem with SAT. And then he produced a proof that is extremely large or not Ramsey number, Schur number 5.
Yeah.
And then yeah, I think his goal is to do something with Ramsey numbers. But yeah, there are certain combinatorial problems for which these methods are useful if you have somebody who's able to translate it into the language of these solvers. Yeah, it's
Any more questions? Well, let's thank Manuel again.
Thank you.
This ends this fascinating talk. Thank you and good night, Manuel.
And thank you for joining and for listening.
Thank you very much. Bye-bye.
Good night.
Thank you. Thank you.